Welcome to the lecture series on two-port networks. This is the fifth lecture where we are going to discuss about properties of symmetrical and asymmetrical network. In the last lecture, we discussed about symmetrical and asymmetrical network. Those who are not watched the previous lecture, I strongly recommend to watch the previous lecture before coming to this lecture. So let's start. In the last lecture, we already discussed that the properties of a symmetrical networks are characteristic impedance and propagation constant. Firstly, we are going to discuss about characteristics impedance. What is characteristic impedance? Characteristic impedance is defined in this way. If we have a symmetrical two-port network, you can read this as 2 bar as a 2-port. This is just my notation for simplicity. So this is a symmetrical 2-port network, and if you are terminating the network with an impedance called ZO, and if you are measuring, this is the secondary port from the output port, from the primary port or from the input port, if you are measuring the input impedance, then if you are seeing the same as the input impedance. So if we terminated the output terminal with ZO, and if I am measuring the input from input terminal, the input seen from the input terminal is also ZO, then such impedance is called characteristic impedance. Since this is a symmetrical network, this is true for other side as well. If we connect same impedance ZO here, and if you are measuring from output side as well, you will get the same impedance. Since it is a symmetrical network, the electrical property won't change. I think the definition it is clear. I'll repeat again. If we have a two-port symmetrical network, and if we connect an impedance, let us say it is ZO. If we connect this impedance, and if we are looking from input side, if we are seeing same impedance from the input side, that means the equivalent impedance of this whole circuit is also ZO, then such an impedance is called characteristic impedance. This is a unique property of a symmetrical two-port network. That means for a particular two-port network, there will be only one characteristic impedance. For example, for this network, let us say 50 ohm is the characteristic impedance. Then there won't be any other resistance value or impedance value for the network which satisfy this condition. That means the characteristic impedance, if we say characteristic impedance is ZO, this is unique. Remember, this is impedance, not simple resistance. For here, for showing the example, I have just shown here a resistance value. Generally, it is an impedance. Impedance is basically frequency dependent. Okay, next we are going to discuss about next property, propagation constant. This is the second property of a symmetrical network. What is propagation constant? Propagation constant is represented by using the letter gamma. Gamma is defined as the natural logarithm of ratio of sending current and receiving current, IS by IR. So what is IS and what is IR? If we have a two-port network, two-port symmetrical two-port network, the sending current is the current entering to the network, and receiving current is the current leaving from the network. Why it is sending and receiving the term? Because the current which is coming here is sending from the source or some other network, and this what the current which is leaving will be received by other network. That's why this is called sending and receiving. So the ratio of these two currents, the natural logarithm of that is called propagation constant. Remember that there will be a phase difference between IS and IR. So generally, not only the magnitude will change. We are sending a current IS. The IR will be of different magnitude. That is clear. May or may not be of different magnitude, and it may also of different phase. That means there will be a phase difference as well. So in general, to represent both this attenuation and the phase difference, or the difference in magnitude and the phase difference, to represent both these quantities, we require a complex number. Or in other words, generally gamma will be a complex number. We can say it as a alpha plus j beta. This is the general representation of a complex number. So what will be e raised to gamma? E raised to gamma will be, this is natural logarithm. If you are taking this side, the natural logarithm will become exponent. So this will be e raised to gamma. From here we can write e raised to gamma will be is by ir. So e raised to gamma means alpha plus j beta. So e raised to alpha into e raised to j beta. This plus I split it to. So e raised to alpha into cos beta. E raised to j beta we know, cos beta plus j sin beta. So this we can write e raised to alpha, and this is a complex number. Complex number, now it is represented like this. You can represent by using magnitude and angle. So if you are representing like this, the magnitude will be square root of these two terms. Square root of this term, two terms will become 1. Root of cos square beta plus root of sin square beta will be 1. Then angle, we can represent angle. So angle will be tan inverse sin beta divided by cos beta. This will become e raised to alpha angle beta. So this is the representation. E raised to gamma. The term e raised to gamma will be e raised to alpha angle e raised to beta. So this is, we know that from a complex number point of view, this is the amplitude term. So that is why this is called attenuation. Alpha is called attenuation constant, and beta is the angle. That's why it is called phase constant. So alpha is attenuation constant, which will give an idea how much the magnitude of the current reduced with respect to the sending current. That means the receiving current, how much it is reduced with respect to sending current. The next one is beta, that we told it is a phase constant. What it will give? It will give the phase difference. That means how much the receiving current lags behind sending current. That information we'll get from beta. Next we'll go to the properties of asymmetrical network. So these are the three properties of asymmetrical network. One is iterative impedance, second one is image impedance, third one is image transfer function. So we'll discuss the first one, iterative impedance. So the iterative impedance is an impedance if we are terminating the output terminal of a asymmetrical network with let us say the impedance as z dash 0 1, and if you are looking from input side, if we are seeing the same impedance z dash 0 1, then this z dash 0 1 is the iterative impedance of port 1, because we are looking from port 1. So iterative impedance for asymmetrical network, this will be different for different ports. If you have two ports, there will be two iterative impedances. Here Z01 is the iterative impedance of port 1. What is the iterative impedance of port 1? if you are terminating a symmetrical network with an impedance, let us say it as Z dash 0, 1, and if you are looking from input side of the network and if you are seeing the same impedance as Z dash 0, 1, then it is called iterative impedance. So what effectively this effective impedance of these two things, that means the network and the terminated impedance, will be Z01. Similarly, same is applicable for port 2. What is the iterative impedance of port 2? Same network. The same way, if we terminate the input side by an impedance, let us say it has Z dash 02, then if we are looking from output of the network and if we are seeing the same impedance, then it is called an iterative impedance of the network, iterative impedance of the port. So for a particular network, there will be two iterative impedances, Z dash 01 and Z dash 02 correspond to each port. Z dash 01 is the iterative impedance of port 1 and Z dash 02 is the iterative impedance of port 2. So for a particular network, a symmetrical network, there will be two iterative impedances. Each represents the iterative impedance of each port. This is an important point. When we discussed about characteristic impedance, it is unique for a two-port network because the electrical properties won't change if you are interchanging the input and output. But in the case of asymmetrical network, that is not the case. The electrical properties will change if you are changing the input and output terminals. That's why here there is an extra one more parameter, that is image impedance. What is image impedance? Image impedance is an impedance of port 1. If we are terminating the port 2, that means the output port of the network, by using an impedance, let us say it as Zi2. And if you are looking from input side of the network, then we are seeing the impedance as Zi1. Then Zi2 is the image impedance of Zi1 with respect to port 1. This also similar to iterative impedance, image impedance as well depends on port. That means for a particular port, there will be an image impedance. For example, for port 1, the image impedance is Zi1 if we connect image impedance of output port at the output. Similarly, same applicable for output port as well. If we are connecting Zi1 at input side, that means Zi1 is the image impedance of the port 1, and if we are looking from port 2, then the impedance seen from the port 2 is Zi2. That is called the image impedance of the port 2. Here also the important point, like iterative impedance, image impedance also port specific. The image impedance of port 1 is Zi1, image impedance of port 2 is Zi2. So for a two-port network, there will be two image impedances, Zi1 and Zi2 represents image impedances of port 1 and port 2. I'll repeat again, the image impedance of port 1 is defined as the impedance seen from port 1 if we terminate the output of the network by image impedance of the output port or port 2. Here in our discussion we are using port 2 as output port. I think it's clear. Similarly, image impedance of port 2, Zi2, is defined as the impedance seen from port 2 when port 1 is connected with image impedance of port 1. So here what we have seen, for representing a characteristic impedance, here we have two impedances. In the case of symmetrical network, there is only one impedance because the property will be same in both the sides. Here to represent same thing, that means in order to represent the impedance, we require two parameters. One is iterative impedance and image impedance. The iterative impedance and image impedance for a particular two-port network will be unique. That means there will be two image impedances and there will be two iterative impedances. These values are unique. Next one is image transfer constant. Before discussing this one, in the case of symmetrical network, we have defined the ratio IS by IR as the corresponding parameter in the symmetrical network is propagation constant. That means e raised to gamma. E raised to gamma is equal to IS by IR, or gamma is equal to ln IS by IR. Like that we defined. So in the case of symmetrical network, ES by ER, that means the voltage ratio and the current ratio will be same. This is clear, right? Why this is same? Because when it is terminated with characteristic impedance, this ratio will be same. That means if it is properly connected network, we'll discuss what is properly connected network. If it is a properly connected network, then the ratio of ES by ER will be equal to IS by IR. Not always. If it is properly connected network, then the ratio will be same. That means if here it is Z0, here also it will be Z0. So IS is the current, here IR is the current, then the voltage at this point will be IS into Z0 and voltage at this point will be IR into Z0. So the ratio will be always constant, IS by IR, because Z0 and Z0 writing ES is equal to Z0 IS and ER is equal to Z0 IR. If you are connecting the input and output by its characteristics impedance, then the ratio of ES by ER will be same. Transfer constant, which is defined as e raised to theta equal to square root of E1 I1 divided by E2 I2. Here E1 is the voltage at the first terminal. I1 is the current at the first terminal. We are not going details about this one, but just for comparison with symmetrical network, where we have a similar term, that is propagation constant e raised to gamma, exponential of propagation constant e raised to gamma is equal to IS by IR. This already we have seen here. Here this also I1 correspond to IS because it is sending primary side current. I2 correspond to this one IR because it is the secondary port or receiving side current. Here the difference, here we are taking E1 into I1. That means effectively this will become power. That's why we are taking square root here. There is a reason for taking this one. Because the ratio of E1 by E2 is not equal to I1 by I2 in the case of asymmetrical network. That's why we are taking like this, the image transfer constant. So just understand this expression alone. We are not going detail about this image transfer constant. Just understand this expression, and it is similar to that of this one, propagation constant in the symmetrical network. Before we are concluding the discussion about the properties, let us have some notes about this two-port network, symmetrical network and asymmetrical network properties. One is this characteristic impedance. We can define the characteristic impedance in other way as well. If you have infinitely many two-port networks, two-port symmetrical networks, two-port symmetrical network, all are same. If you have such infinite number of networks interconnected together or cascaded together, and if you are looking from this side, from the input side, or from any of the port, this is up to infinity. So the impedance what is seen from here will be the characteristic impedance. Why it is characteristic impedance? Because if you are taking from network from here to up to infinity, because this is an infinity network, if you are removing one from here as from the starting, the resultant network also will be an infinite network. If the seen impedance from here is ZO, then the seen impedance from here as well ZO. So what we can say here, the output is, it's like an output is terminated at ZO, and if we are seeing from here, we are getting the same impedance, right? So if it is an infinite network, then the impedance seen from the input side is the characteristic impedance. That is one of the point we have to note. So characteristic impedance is the input impedance of a symmetrical network cascaded together infinite number of networks. Second point is properly connected network. Properly connected, or we can call it as properly terminated network as well. Properly connected or properly terminated network. What is this network? Properly connected or properly terminated network means, in case of symmetrical network, if the network is terminated with ZO and the source connected to the network is symmetrical two-port network, that is clear. The source connected to the network has internal resistance or internal impedance of ZO, then this network is called properly terminated or properly connected network. Here the output, no, it's not resistance, generally impedance. Output impedance, that means the terminated impedance, and the connected impedance, that means the impedance of the internal resistance of the network and the impedance which is terminated. If both are equal, then we can tell it as a properly connected symmetrical network. In case of asymmetrical network, instead of characteristic impedance, there we will use the term of image impedance. That means if we connect output port of the two-port network with Zi2, image impedance of that port, and if we are connecting a source to the network with internal impedance of Zi1, then this is called a properly connected network. You can relate this term with respect to the maximum power transfer theorem, because if we want to transfer maximum power, the impedance should be matching. So there won't be any power loss. If you are not power loss, there will be some power loss, but it will be the maximum possible power which can deliver to the load if the power transfer theorem is satisfied. That means the impedance and the terminal impedance, the source impedance and terminal impedance are matching. In that way we can look this network as well. If you are looking from here, what we are seeing, ZO. So basically if you are rewriting the first network, we have a source and we have a ZO here, and if we are looking from here also, this complete network we can replace by using an impedance of ZO. So what will happen? This is this satisfies the maximum power transfer theorem, right? If it is resistance, then the maximum power will be delivered from here to here, because the both resistance should be equal, then only the maximum power will be delivered. Similarly, if you are looking from output side, output also we can sending the signal from output side. So from here we are sending the signal. So if you are rewriting that diagram as well, what we can see, output side, complete output side we can rewrite as a ZO, and it is terminated with ZO. So what is the power we are transferring will completely get to the load. That means the maximum power will get to the load. So that's why it is called properly connected or properly terminated network. Hope this is clear. So let's close this section. See you in next section.